Hello, everybody. Welcome to this week's Green Bank Community Zoom. No announcement from the observatory, but I do have a personal announcement to make. So over the past year, I've been through quite a lot. As you know, I've had major surgery and medical treatment. While I was recovering, I wrote a paper, and I was very happy with that paper. And I became a grandfather to what I objectively know is the cutest baby who was ever born. So I am doing well so far in my recovery. In fact, I had a CAT scan on Monday, and I'm still clean. So that's all good. But I do want to take advantage of my good health. And I realized how much I love doing the science, and I have a lot more science that I'm eager to write and a lot of data to analyze. And I want to spend some more time with my wife and my family. So I decided to retire, and my last day at Green Bank will be February 7th. My wife Jennifer and I will be returning to Sydney, Australia, and we have an apartment in the Piermont neighborhood, about a 15-minute walk from downtown. I will have an adjunct appointment to GBO and NRAO. The apartment is lovely, and Australia is lovely, and Sydney is lovely, and I'm really looking forward to spending time in Australia doing my research, spending time with my family, and doing my photography hobby. Sydney is a very beautiful city, and there's all sorts of interesting Australian birds and creatures. So I look forward to spending some time out in the bush, photographing the kookaburras and the splendid fairy wrens and the rosellas and all those wonderful Australian birds. So this is the best job I've ever had. It has been an honor to work with the folks here at Green Bank. They've been fantastic. They're a very dedicated and very talented group. I'm proud of the work that we've done here at Green Bank and the great science that we've enabled together. I'll miss the staff very much, and I'll miss the community very much. So thank you for your support, staff, and thank you for your interest in the observatory by the community. Please continue to do the good science. I won't disappear. I'll just be down under. So with that, I will pass it off to Dave, who will introduce today's speaker.
Thank you, Jim. It's our pleasure today to have Gabi Wenzel from MIT, and we're excited to hear about the new astrochemistry discoveries that she'll be talking to us about with the GBT. So go ahead and take it away, Gabi.
All right, let me share my screen right here and start the slideshow.
Looks
and
good.
just like one last check, you can see everything.
Yep.
Perfect. Okay. Wow, yeah, exciting news, Jim. Congratulations on your retirement, and all the best for Down Under. And thanks so much for having me and letting me present these exciting results that came out of the GOTHAM survey earlier this year. So I'm going to talk about interstellar PAHs and the discovery of 3 cyanopyrene isomers in TMC-1. And when I start these presentations, I usually dive right in with a slide like this that is now outdated, which shows the known interstellar molecules that we have. We know many small ones, 2, 3, 4 atoms. We usually call the ones that are above 6 atoms complex molecules, but I really want to concentrate on the ones here, the category 13 plus atoms, and namely mostly the polycyclic aromatic hydrocarbons. When we look at the detections over the past years, of course, we wouldn't know so many molecules in space if it wasn't for all this work of the radio telescope. So I want to give a shout out here. So ever since, let's say, the invention of radio astronomy in the 40s and then 60s, we're detecting 4 detections or molecules per year since the 2000s, and GBT is working hard on that. It's been 6. And I put myself here on the slide whenever I started my PhD in 2017. It's not really a causal or correlation here, but we're looking at 20 detections per year recently. And I just put that here because I want to say it's a super exciting time to be an astrochemist in these years. If we look at PAHs, those larger molecules, we're looking at them or thinking about them in space, basically like on the same time scale. So this is the same plot that I'm just marking out whenever PAHs came into the picture. So we found them in meteorites, we've seen them in comets. I'll talk about the PAH model just in a second. And also like a big outcome of this GOTHAM work with the GBT was the first unambiguous pH detection in 2021, which was here with the cyanonaphthalines that I'm plotting both here, and also the cyanoindene and its bare pH indene. But why are we caring about pHs so much? And this is really because pHs have been proposed or thought of like as part of interstellar dust. This is a photo I took last year with my iPhone 12 when I was in Green Bank. So thanks again for having me over there. And when you look into the sky, we can see these dark patches in our own Milky Way. I'm changing a little bit the resolution here. So here again are the dark patches. So interstellar dust is really something that's absorbing or scattering UV-vis light. If we now change the wavelength into the infrared, we see that these same patches are now irradiating very brightly in the infrared. And people are using this to define interstellar dust and model this. So I picked here one of those models that I'm setting up here, modeling the extinction curve, so the absorption and scattering of the UV-vis light, and also the emission curve with the pH features shown right here. What people usually account for interstellar dust are the amorphous silicates, large amorphous carbon, small amorphous carbon, and pHs. So pHs are really considered the smallest dust grains, so to say, on the sub-nanometer scale. I'm plotting these here because usually we're looking at pHs that are a bit larger than the ones I've talked about so far, but I will come to this just in a second. I want to first talk a little bit about the pH model that was introduced in the 80s, and that was very much based on infrared spectra we saw towards many different regions in the space, astronomical regions. So these are attributed to the vibrational modes of pHs, and if we look at a pyrene molecule here in its CH stretches, we can locate these here at like the 3.3 and 3.4 micron area. And if I go through the spectrum at these bright features, we can associate them all with different vibrational modes of this family of molecules. However, we can't use these for an unambiguous detection, but we can still learn a lot from infrared spectra. And that is a very ongoing kind of research right now, especially with the James Webb Space Telescope, from which I've taken a photo of the PDR at the Orion bar right here. And if we zoom in this region, we can see here a star irradiating some sort of molecular cloud from the left. These photons are penetrating, and we can obviously then distinguish here between H2 regions, H1 regions, and something that we call the molecular region. So something where dissociation of CO or O2 becomes negligible. And where we see the aromatic infrared bands, this is very much here at the ionization and dissociation fronts. So this is really where people have looked at pHs so far. And this is really because if you have a pH and you're thinking of it to be somewhat isolated and close to a hot young star, it's going to be irradiated with a UV photon. Maybe there will be one a day, and it's going to be excited. And this excitation will lead to some sort of relaxation. And the relaxation channels that we know of can be ionization, which is by far the fastest channel, dissociation, which we both count under destruction channels, and also the radiative cooling, by far the slowest of the channels, under which is also the infrared cooling, which will result in the aromatic infrared bands. If we now look at the stellar life cycle, or the, as I put it here, life cycle of cosmic dust, so life cycle of pHs question mark, of course, these are very closely related to each other, and we can populate this life cycle with knowledge that we have of where pHs are. However, their life cycle through this is not very well understood. So we can somewhat agree that pHs will be born in like a star death scenario, so on the outflows or circumstellar envelopes of some AGB star. And this is really something we know here from Earth and combustion chemistry. We then just spoke about the aromatic infrared bands that we see at these ionization dissociation fronts of the diffuse ISM. We're also seeing pHs in emission, again in the infrared from disks, and we have found in meteorites and comets. So how does this connect? Are pHs able to survive? Because people in the astrochemistry community were under the impression that no, they do not. And in fact, there are models that place pHs of size between like 30 and 50 carbons and smaller than that to not be able to survive any harsh interstellar environments. So that's why I put pH destruction over here. However, we know that we found naphthalene or cyanonaphthalene in a dense cloud, TMC-1. So how did this molecule get there? And we're trying to answer these questions with the GOTHAM collaboration, and this is what we're going to concentrate now in the rest of the talk. So to move away from this, we took an asteroid to help us actually to like what to do next, so to say. So I will quickly summarize what in this paper by Zeichner and co-workers published in Science last year was found. And they have investigated 5 pHs in total in Ryugu, in this asteroid, which maybe I should take a step back. So Ryugu, there was the Hayabusa 2 mission, and we actually do have return samples brought back from that asteroid here on Earth that can now be investigated with like very high sensitive laboratory techniques, which is fantastic. Right. So after pHs that were investigated in this paper, we have a subset of 5 here, which are like naphthalene, phenanthroline, anthracene, fluoranthene, and pyrene. Broadly, we can distinguish them into 2 rings, 3 rings, and 4 rings. And in this paper, Zeichner co-workers were able to even detect carbon-13 substituted isotopic loads, and even the doubly substituted ones. And from this isotopic analysis, they could deduce that these 3-ring species, here these acene like anthracene and the CPV-shaped phenanthroline, must have been formed at a high temperature process. So something that might be consistent with circumstellar environments, something above 1000 Kelvin. However, they also found that the 2 and 4 ring pHs, naphthalene, fluoranthene, and pyrene, must have been formed at some more kinetically controlled process. So something that will be more in line with the cold dense interstellar medium. And they're discussing if some in situ formation in the ISM is possible without proposing any exact routes. And indeed, when we look at TMC-1, our favorite molecular cloud, we have detected the pHs there before, and we do indeed see the 2-ring species cyanonaphthalene. So this is in line with those findings in this Ryugu paper. So we went on and wanted to see, so what then about 4 rings? So this is pyrene. It's, I would like to say, like a prototypical compact pHs. It has 4 rings that are all touching at least 2 other rings. And it's highly symmetric. So we cannot look at this with rotational spectroscopy or radio astronomy. So what we do is we pop on a CN group, and we will introduce a large permanent electric dipole moment. In this case here on the 1 position that we now call 1 cyanopyrene. I want to highlight quickly the laboratory is also where I'm sitting in the laboratory. I'm a laboratory scientist, and the majority of this work was done here in laboratory with this machine over here. And on the slide here, I'm showing you 1 cyanopyrene when it's pressed into how I call it sample rod. And here you can see what happens when I shoot a laser at it. So we're basically doing a laser ablation with this molecule, which is a solid. So bringing it into the gas phase is slightly challenging, but we made it work. So we're shooting the laser. We can really ablate with each laser pulse material that we then push into our cavity-enhanced Fourier transform microwave spectrometer. That is right behind me here. So here we have a nozzle that will pulse some inert gas and take all the cyanopyrene into the cavity. We will excite with a microwave pulse. We will turn off the excitation, and then we will record the free induction decay of these molecules that we then can Fourier transform and collect the radio signatures, so to say, of this molecule here in the laboratory. I'm also showing you where the laser interacts. So that's happening in vacuum. And I'm also putting here our nozzle with the laser ablation. If you squint your eyes, you can see like the little ablated molecules down here. In order to record a spectrum in the laboratory, first would want to predict where we're actually looking for. And those cyano pHs, they have very dense spectra. So this is the prediction that I have run with some quantum chemical package. And those are the lines that I have recorded in the laboratory. So you can see there's a very dense spectrum, and I am not showing you as many lines, but actually those are 300, on the order of 300 lines that we recorded for this molecule that we then can use to fit. And this is the result. And now you're telling me, Gabi, this looks all the same, like I can't see anything. If we zoom in, we can see that indeed the prediction was super close, like they were kind of right on, but they're still really far away from any chance of astronomical detection. So like one takeaway that I would want to give you today is really like, we still need to measure them in the laboratory. Right. Now we're going to your favorite subject, the GBT. So I'm fairly new still in radio astronomy and the GBT. In fact, I got my observer training only last year. And this is a data set that was collected in the GOTHAM collaboration over the past, I want to say 8 years. So this is 1,500 hours of integration. It has been published before on the DR42. And we have hence collected some more hours down here in X-band, where I've also contributed myself. So I was very excited to be able to do this. And yeah, stay tuned for what we're getting out of that. So yeah, but I want to show you here this amazing spectrum. All the receivers that we were able to use, or the bands that we were able to collect, and where our cavity instrument is operating, which is really directly overlapping with what the GBT can do for us. I want to very highlight though the intensity scale here, because mind that like these beautiful lines, they're all here on the Kelvin scale. However, if I now simulate the cyanopyrene signal under TMC-1 conditions, I get really, really low and into the millikelvin scale. So we really need those low noise floors for us to be able to get any signals out for these large molecules. What I'm showing here as well is the noise floor that we have in the data so far, and like a couple windows where maybe single line detection would be viable for us with this data set and this molecule. And indeed it was. So these lines are not bright, but they're there. So we're seeing here 9 one cyanopyrene lines. We were super happy when we saw this. So this was really, really exciting. And then if we apply our stacking and matched filtering analysis, where we basically extract a window around each frequency in frequency space calculated into velocity space, and then stack it in velocity space. And we do this with the GOTHAM data, so the astronomical data, and also with the simulated cyanopyrene data. We could overplot them as I'm showing it right here, and run like a correlation function on this, and we get so our impulse response, so the final significance of our detection of around 14 sigma for the 100. For the 150 brightest signal to noise ratio lines for one cyanopyrene. Okay, when we look at the context here again with the Ruby results, we can in fact say, yeah, 2 and 4 ring PAHs have been detected in TMC-1, amazing, possibly a low temperature formation route that we don't know. 3 ring species, at least those linear ones, have not yet been seen in TMC-1. I want to hint though that also very recently, Pepe Chenichero and his team have detected cyano-ace naphthalene. So this is a 3-ring molecule consisting of these 3 rings. So also a more like compact ones, where each ring at least touches the other 2. We also wanted to compare to the abundances that were found in Durigo. So the Durigo result had pyrene by far the most abundant molecule. Its isomer fluorine was a close second, or actually not so close second, but a second in that. And then the others are like rather close to smaller ones, with 0.2 parts per million for the naphthalene. So when we compare this for the PAHs that we have found with the GOTHAM collaboration, we can see that we're actually getting like 1.5 10 to the 12 inverse square centimeters, which is as much as both these naphthalenes here combined. But how much pyrene is there? So this was the molecule we were interested in the beginning, right? That we just cannot radio astronomically observe because it doesn't have a dipole moment. So this is based on also experiments that have been performed by one of our collaborators, Rosa Cook, during her, I want to say, postdoc time in France. And basically, what we can use is CN addition to the bare molecule. So we're having here benzene, and in their laboratory, they could investigate the addition of a CN group and then hydrogen abstraction from this molecule. So we were trying to get something out of this, like a CN over H ratio. But before I get into this, I want to shortly tell you that maybe you paid attention on this first slide, where I showed you the pyrene, that we have multiple locations where we can attach the CN group. So looking at the benzene, they are all identical. However, at the pyrene, we have 3 different sites where we can attach, and we can make 1 cyanopyrene, we can make 2 cyanopyrene, and we can also make 4 cyanopyrene. And I don't want to bore you like with the data analysis and everything. So you need to believe me when I tell you we found all of them. You can also look it up in our recent publication with a column density ratio of approximately 2, 1, and 2. So we wanted to see if this is expected or not. So one hint are those sites that we can look at. So for the 1 and the 4 cyanopyrene, we have 4 identical sites, or equivalent sites, I guess, where we can make the same isomer. However, for the 2 cyanopyrene, we only have 2. So when we look back at these experiments and also observations, we can't really do this experiment for pyrene. It's too big, it's too hard. But we can use models and we can calculate those CN addition rates. And this has been done in this plot over here. And we're basically using here a model to plot the CN over H ratio for different times over the different rates that we could expect. And we do have, in fact, 1 PAH for which we have an observation, which is the bare indene versus its cyanoderivative 2-cyanoindene. So this data point is here, this little diamond, or in the zoom in, it's over here. And the rates that we could calculate for the pyrenes, the cyanopyrenes, are roughly 2, 1, and 2, 10 to the minus 10 cubic centimeter per second. So if we look at this plot here right now, we can go to 1, and we will come out at 0.025. So this will make around 40 times cyanopyrene. And if we go up here to 2, and we're going back up this plot here, we come around to 0.05, so roughly 20 times the amount of cyanopyrene. So if we use the column densities that we derived for these, we all come to a value that's very close to 3 times 10 to the 13 inverse square centimeters of pyrene abundant in TMC-1, which actually is really surprising that we find so much of it. Because if we compare this here to a very famous family of molecules, the cyanopolyenes, that have been detected in TMC-1, we see that usually with this is number of carbon down here on the X scale or X-axis, we usually see a decrease with increasing complexities. So the molecules get bigger, we see less and less of those until we see like a really big drop here between the HC9N and the HC11N. Whereas if I plot now the aromatics for you, and those are all the observational data that we have so far, where I am combining all the isomers of cyanopyrene and all the isomers of the cyanophthalines in one data point here, we see that there's no decrease visible here. And in fact, we actually see an increase. I'm also putting the pyrene on here without error bars because it's a guesstimate for us that we put. So putting error bars here would a little bit distort this picture. However, like the increase seems to be there. So there might be some sort of like overfold here and something else going on that we have not understood yet. And yeah, with that, I want to come to my conclusion to summarize that we've found 3 isomers of cyanopyrene in TMC-1. We're super excited about this. We derive a somewhat high abundance for pyrene, 3 times 113 inverse square centimeters. And the cyanopyrenes so far with the GBT have been the largest molecules that have been detected with radio astronomy to date, which in itself was really amazing to do. So I just again want to give a shout out to the whole team and to the whole GBT staff making this possible for us. So when we move on now and we want to answer those questions about the formation in situ or inheritance throughout the stellar life cycle for the PAHs, we really need to go further and kind of detect more intermediates of these PAHs and also try to put a size constraint on them and just see what we got. So again, thanks so much for all the time that you have been giving us, and we hope for more, so we will apply for more. And it's been really, it's been just really the beginning of detections of such complex molecules in space for us. So yeah, with that, I would like to thank all the funding that we received, all the support again, all the GBO staff, and all my co-authors on this big project. You possibly know many of them personally, and I'm very happy to take their questions.
Thank you very much, Gabi, for this exciting talk, and congratulations to you and your team for this discovery. I'd like to remind all the participants you can put your questions in the Q&A, and we'll go over them. So we have some questions that have come in during your talk already. It starts off with an editorial comment from William Forrest, who points out that he, Gillette, and Merrill first discovered PAHs in the 1973 in a planetary nebula, though at the time they didn't actually know what the 8.6 and 11.3 micron broad emission features were originated from. But then he follows up with a question, and this is sort of an appropriate question. Isn't the density too low for Paul formation in the diffuse ISM? So I guess it's a question on how these things form, because we would think they'd form in more dense, really hot environments. So now we see them, obviously you're detecting them in the diffuse ISM.
Yeah, I'm happy to receive these questions, and I do have like very quick backup slides for that, because so the broad answer is we just really don't know. If we look at models, astrochemical models of the region, TMC-1, we can already not explain the abundance of cyanonaphthalene that has been found. So here on this plot, this is the cyanonaphthalene evolution over time, and those are the observed values. So even with inclusion of some starting material, those do not match. So there is something that is not understood yet at all in the formation of these PAHs in situ. And we don't know them. So when I go back to what I just showed, there are a couple of routes that we know that can form PAHs. One here is called HACA. It's hydrogen abstraction and acetylene addition. So here we're basically needing where are the barriers here, like 15 kilojoules per mole, 24 kilojoules per mole. So this is really like a hot route. So this can't really happen in TMC-1. Whereas the HAVA, where we instead of acetylene, we're using now vinyl acetylene addition. This route can form some PAHs at low temperature. However, it cannot form pyrene. So we really do not know what is happening. So what we're aiming for is, more time to see more of such complex molecules signatures in TMC-1, and to then with those get clues of which routes can happen. And it's also basically like playing the ball back to the astrochemistry community. Like we need to come up with other routes that can happen more efficiently for in situ formation, or maybe the whole inheritance thing will come into play. Yeah.
Okay, thank you. A question, what is the ratio of pyrene to cyanopyrene abundance in TMC-1? Do you know the ratio?
Right. So this is basically then what I would put here on this slide, where we basically would assume pyrene to be 20 times more abundant than the 104 cyanopyrenes, or 40 times more abundant than the 2 cyanopyrenes. Yeah.
Okay. Can any of the carbon-13 substituted PAHs be identified from the spectroscopy data?
So yes and no. So in the spectroscopy data, certainly yes. In this instrument is sensitive enough for us to detect carbon-13 substituted PAHs. It is going to be a big effort, because if you look at the structure, there are many like everything becomes the moment you put in the cyano group, everything becomes what's the word? Oh God, it's not identical, but the opposite. So unique. So all of these sites are individual. So we have lots of molecules to look for. So then the substitution, if we think about this in space, this will be a very faint and very dilute signal. So we're currently working on a technique which we call stack of stacks, where we might be able to see signatures of carbon-13 substituted PAHs when we consider them as a family, but not just one individual one. Yeah. So this is a big project that will help answer, or would hopefully help answer lots of questions in the future, but it's gonna take lots of effort.
Okay. Another question. Can your presumed pyrene abundance explain the IR PAH emission from the TMC-1?
That is an excellent question. I have not looked so much into IR emission from TMC-1 myself, so that is something I would need to read up on, and if there are any similar bands. In general, I would want to say no, because TMC-1 is fairly cold, like 5 to 10 Kelvin is what we assume, or around 10 Kelvin maybe. And all this IR emission that I have presented in the beginning of the talk, these aromatic infrared bands, those are really like highly photon penetrated regions, photodominated regions. So those are hot bands, hot PAHs, far above 1000 Kelvin, that absorb this energy and re-emit the energy in the infrared throughout their vibrations. So like a 10 Kelvin spectrum would look much narrower, but I mean, this is what we do in high resolution infrared spectroscopy in the laboratory as well, like looking at colder PAHs. But at the absorption and not at the emission. So there's still also a mismatch between laboratory data and observational data that will be very exciting to unravel in the next decade or so.
Okay. I have a question here. What are the prospects, and I'm gonna mispronounce this molecule, to observe cyanopyrene?
Cyanopyrene,
yeah, and TMC-1. So I'm not familiar with this. So
yeah, cyanopyrene, I haven't put it on the slide, but it's basically another 3 rings around here. So it's becoming like a highly symmetric molecule. It will have 7 rings. We also call it superbenzene, which I think is a super cool name because it's benzene with a lot of benzene rings, 6 benzene rings around it. We want to do this one. Yeah, it's very high on our list of molecules that we will ask for more time in lower bands at the TBT this coming season. Yeah.
the lower bands like X and KU, or
yeah, exactly. Yeah.
okay, out of curiosity.
Yeah. Yeah. Cool. Stay tuned for our proposals. Yeah.
Okay. Do we have any additional questions? Okay. Well, I'd like to thank you again, and for that. I mean, I find these results very exciting. It's nice to see everything coming together from the Gotham team. So we really appreciate seeing all these results. So thank you very much. Our next community Zoom, we're taking a little break for the holidays, will be January 15th, and it'll be a radar presentation by Bruce Campbell from Smithsonian Institute. So I'd like to wish from the observatory everybody a Merry Christmas and Happy Holidays. And thank you again, Gabi. So goodbye, everybody.
Yeah.